Okay. Hold on a second, Gianjo.
Yeah, I have not seen your screen yet.
Yeah. This. Do you see?
Okay, there you go. Yeah,
okay.
Perfect. Yeah, there we go.
Okay. Okay. Well, good evening to everyone, and thank you very much for inviting me to give this seminar on artificial intelligent geothermobarometry of volcano plumbing system. This, let's see, hold on a second, if I make, okay. This research project was born thanks to the collaboration with two colleagues of mine from the Department of Physics and Astronomy, which are Lorenzo Chicchi and Duccio Fanelli, and one colleague of mine from the Department of Earth Science of the University of Florence, Luca Bindi. And the two colleagues from the Department of Physics developed the machine learning code, whereas Luca and myself have worked on the selection of suitable clinopyroxene composition to train the machine learning algorithm. What has been the starting point? Since the excellent work of Cashman and co-works in 2017, where she demonstrated the existence of multiple reservoirs within the crust feeding the volcano plumbing system. The starting point has been then to try to find a way to decipher the depth of this magmatic reservoir, and so we use a geothermobarometry, which is crucial to assess the intracrustal plumbing system of volcanoes. What I will talk today will be about this point: why choose clinopyroxene, the machine learning strategy. Even if at this point I'm not. I cannot tell you very much because the machine learning code has been developed by the two guys of the physics department. Then I will talk about the input parameter, the training, validation, and test results. Then I will present the geothermobarometer that we have developed and the app, which is available to everybody on internet. I will make a few comparisons with a geophysical survey of volcano plumbing system, and then I will present some case study, which are work in progress, on Stromboli, Campi Flegrei, and Etna. Why we choose, can you see, okay, why we choose clinopyroxene? Well, mainly because it's very common in a wide variety of volcanic rocks, from mafic to evolved composition, and the variation in chemical composition of clinopyroxene has long been used to estimate temperature and pressure of volcanic plumbing system since the beginning work of Putirka in 1996, and then the recent work, the rather recent work of Nive Putirka in 2017, especially on pressure. What is the machine learning strategy that we adopted? We have not been the first to use machine learning to assess pressure, temperature of volcanic plumbing system. The first one has been the group of Petrelli, Higgins, and Jorgensen from Umbria. I know that Petrelli has been already at your university and gave some talks. And Higgins and Jorgensen are from the University of Geneva, but they work together. The machine learning strategy has been random forest, whereas our machine learning strategy has been different. It's a deep learning feed-forward neural network. And I cannot tell much more, as I said, about the differences between these two machine learning strategies. But what I've been working on together with Luca is on the input layer. So this is really crucial to critically assess the result from the machine learning code that you can develop. So what you use to train the machine learning is very important. And I worked especially, particularly on the input layer. We started to select a database from the library of experimental phase relations, complemented. Sorry? Oh, sorry. So we started to select the database from this library of experimental phase relations, complemented with recent experimental meteorology data. And we end up with more, with some 16,700 liquids and clinopyroxene pair. We limited our database to pressure of less than 10 kilobar because we were interested in a volcano plumbing system. To this database, we applied some filters on clinopyroxene, mainly because we wanted to evaluate the quality of the analysis. So we limited the analytic closure to this value, 97.5 and 102.5 weight percent. We recalculated the chemical formula on the basis of 4 cations and charge balance to estimate bivalent and trivalent ion. Then we applied also this filter, wollastonite limited to 20, between 20 and 55%, ferrocylite between 5 and 50%, the J parameter, which is twice the atom of sodium per formula unit less than 1, then the tetrahedral side in between this range, 1.95 to 2.05, as well as the X and Y side of clinopyroxene. Then we limited, we applied the filter on the basis of the amount of silicon atoms per formula unit less than 2, and the total charge in between 11.95 and 12.05. And we end up with some 5,600 clinopyroxene, mainly comprising within the quadrilateral of the clinopyroxene composition. In other filters, which apply to the clinopyroxene, we recalculate the clinopyroxene components following this order from calcium, titanium, cerma to ferrocylite, and we the sum of this component has to be in between 0.95 and 1.05, and also at the end of this process of clinopyroxene selection, we end up with 5,600 clinopyroxene. And then we go to the machine learning algorithm. We use as input parameters all this component of the clinopyroxene that we had recalculated, plus the liquid composition from the library of experimental phase relation, plus the pressure and temperature, which are known. And we train this the machine learning, the feed-forward neural network using this parameter to obtain pressure and temperature as output as a function of a clinopyroxene component. During this process, we use 80% of the database for training and validation for temperature and 20% for test. Whereas for pressure, we use 95% of data for training and validation and 5% for test. Why this difference? Because as you can see here, pressure is not distributed uniformly across the range we investigated between 0 and 10 kilobar. So to maximize the chances that sparsely populated pressure range were adequately represented, we use this 95% for training and validation and only 5% of the data for test. And here you have the first result on the validation data that we used, the distribution of P, on P, the error distribution of P, that as you can see is much lower where you have more data at 1 atmosphere, 2 kilobar, 4 kilobar, 8 kilobar, and 10 kilobar. In between this value, the error tends to be much higher, but in most cases is always less than 1 kilobar. So it's a good result, even if this pressure range are not very well represented within our database. Now I will show you the result of the test set result starting from temperature. I don't know why. Okay. And on the left diagram, you have the validation set result using only clinopyroxene, whereas on the right-hand diagram, you have the validation set result using clinopyroxene plus liquid. And as you can see, in both cases, the error is pretty good, much better, of course, in the clinopyroxene liquid pairs, which is plus or minus 5 degrees centigrade, whereas using only CPX is a little bit worse, but it's 12 degrees centigrade. And the same result using pressure for the test set result of pressure. And also in this case, on the left diagram, you have the result only from CPX. On the right diagram, the result from CPX liquid pairs. And also in this case, as much as for temperature, the error is much better using CPX liquid pairs and is a slightly higher using only CPX. The correlation, however, between using only CPX and CPX liquid using for both temperature and pressure is very good. You have a correlation coefficient greater than 0.97 in both cases for temperature and pressure. So what we decide to do is to use only clinopyroxene geothermobarometry. And this is because it's very critical, because of the thermodynamic equilibrium between CP clinopyroxene and host magma is rarely attained, given the complex structure of volcano plumbing system with the occurrence of multiple transcrustal magmatic reservoirs where input of fresh magma interacts with resident magma and crystal masses. And here is an example from the Campi Flegrei, 2 periods of eruption at Campi Flegrei in Italy, the Neapolitan yellow tuff and the Campania Indian bright, where you can see that the equilibrium between mg number of clinopyroxene and mg number of the liquid, which should be around 0.27, it's not attained, or it's only rarely attained in the analyzed clinopyroxene. And this is the partition coefficient between clinopyroxene and melt of iron and magnesium is not the only thermodynamic equilibrium that must be satisfied, but we have also this other parameter, the difference between observed and calculated from liquid, a difference between this component, diopside edinburghite and statite ferrosilicate and calciothermite. And so since this equilibrium are not easy to be attained, we decided to use only clinopyroxene geothermobarometer, even if you have a slightly higher error on the validation set. And this is the result on the test result. That is the data set which has been kept aside from training the neural network. So these are all also data from the library of experimental phase relations, but which have been kept aside from training the neural network. This is the result on temperature from 650 to 1450 degrees centigrade, and we have an error plus or minus 28 degrees centigrade, and these are the result on pressure. Also in this case, we have very good result, and the error is 0.9 kilobar. Remember that in the case of temperature, you have the 20% of the data set used as a test result, whereas in the case of pressure, only 5%, because of the reason which I explained before. And eventually, we arrived to the presentation of the geothermobarometer that we have developed. Here you can find the connection to the app we have developed, and you will have this structure. It's very simple. You have to put the chemical composition of clinopyroxene that you have determined using the electron microprobe, and you can also download, of course, an input file form. Then you drag and drop the file here, and you process the data to have a prediction of temperature, pressure, and also the clinopyroxene components according to the order which I mentioned before. And this is a comparison between our feed-forward neural network with the random forest result obtained by Higgins et al. In 2022, which, to our knowledge, are the best result obtained so far using random forest. And as you can see, the error on both temperature and pressure are much better with our feed-forward neural network. We have plus or minus 28 degrees centigrade for temperature versus 57 degrees centigrade, and plus or minus 0.9 kilobar for pressures versus 2.3 kilobar. So I think we obtained a much better prediction of temperature and pressure on the plan-based system of volcanoes. And now what we did, we tried to use our geothermobarometer to estimate the depth and also the temperature, but we are particularly interested to the depth of the plan-based system of 5 active volcanoes in Italy, and make a comparison with geophysical survey. So where this geophysical survey located these magmatic reservoirs within the crust. In this example, we had made no distinction among the different eruptive periods of this volcano. So there could have been difference in the magmatic reservoir depth between the different periods of volcanic activity, but in this example we don't make any distinction. The 5 Italian volcano we work on were Etna, Volcano Stromboli, Vesuvio, and Campi Flegrei in the southern part of Italy. And I will show you the result only on 2 out of the 5 active volcanoes, just for time, but if you want, I can show you the result also on the other volcano which are not presented now, but you can find the result on the paper which has been published on Earth and Planetary Science Letter. But let's go to see the result on Volcano and Vesuvio, just to make you an example. So what the geophysical surveys made on Volcano established that the internal structure of the plumbing system consists of 2 major storage zones, and a network of conduits connects this magma accumulation reservoir. there is a minor shallower zone beneath La Fossa Cone, which is part of this volcano, which is located at 0.4 and 1.6 kilobar. And here in the prediction we made using clinopyroxene, this is the location of this of the first minor shallow reservoir. And then there is another shallow major magmatic reservoir located between 2.2 and 3.7 kilobar, which appear the biggest reservoir contributed to clinopyroxene composition. And then we have the signal of this also another reservoir in between 4.8 and 6 kilobar, which should be indicated by this kind of clinopyroxene. So as you can see, the prediction of pressure using the geothermobarometer we have developed is consistent with what has been determined using geophysical surveys. If you go to temperature, the temperature estimates of volcanic magma have a wide spectrum of range because the compositional range of magma are basalt latites and trachytes and rhyolites. And for latites, they have estimated temperature ranging between 1027 and 1080 degrees centigrade. For trachytes, 1004 and 1050 degrees centigrade, and for rhyolite, 955 degrees centigrade. The kernel density estimated we made using the prediction we obtained using GAIA are consistent with the estimate and reveal three major peaks, as you can see. One peak is a 1000 degrees centigrade for trachytes. The other peak is a 1050 degrees centigrade for latite and trachytes. And then there is another peak, which is an 1125 degrees for basalt, which is not included in the above mentioned estimates, but in our case, we have clinopyroxene revealing also this other peak at higher temperature. Whereas what we don't see from this prediction is the temperature of rhyolite at 955 degrees centigrade. But this is mainly because this temperature, as you can see here, has been determined using the plagioclase liquid thermometer. And so it cannot be established by our clinopyroxene geothermometer. This is the reason why we don't see in this kernel density estimate the temperature pertaining to rhyolites. If we go to Vesuvius, also in this case, the geophysical survey have considered that there are a number of magmatic reservoirs randomly distributed and interconnected to each other at 0.8 and 1.9 kilobar, which is this peak that we observe with our kernel density estimates. And then there are a number of magmatic reservoirs interconnected to each other between 2.5 kilobar up to the mantle crust transition at 7.5 kilobar. And these are all these clinopyroxene, the prediction made by our clinopyroxene. In terms of temperature, the estimates of temperature of the Vesuvio volcano have been related to three stages of evolution. An initial stage with mafic magma at 1100 degrees centigrade of temperature, a young stage with evolving mafic magma at 1050 degrees centigrade, and a felsic magma in between 850 and 900 degrees centigrade. And then we have a final mature stage with evolved mafic magma at 1050 degrees centigrade, with a stratified upper portion of felsic magma at 800 and 950 degrees centigrade. The prediction we obtained using our geothermobarometer yields, as you can see, a major peak in between 1025 degrees and 1125 degrees centigrade, which are the 75% of the data, and two other minor peak between 850 degrees centigrade and 1000 degrees centigrade. And as you can see from the estimates made, independent estimates made for the Vesuvio magma, the high temperature peak is consistent with temperature estimates of the mafic magma, trachybasalt and basanite, which feeds the magmatic reservoir of Somma Vesuvio, and the evolved mafic magma, the tephrite, whereas the other minor peaks correspond to the temperature of evolved felsic magma, latite and phonolite. Now, let's go to some work in progress which are currently doing. So I will present you some preliminary results. And these are work in progress has been concentrated on PT pressure and temperature estimates on specific eruptive period at Stromboli, Campi Flegrei, and Etna. About Stromboli, we are collaborating with Lorella Francalanci, which has been working on Stromboli since more than 30 years. And Stromboli is a volcano in the Aeolian arc, which has the largest composition of variation of all the Aeolian arc volcanoes. And here you can see the variation, the compositional variation exhibited by the Stromboli volcano. It consists of 6 eruptive periods from something like 85 kilo years ago up to the recent, from 5 kilo years ago to the recent, and the result, the preliminary result which I will show you, will concentrate on the recent period of activity, which erupted as shoshonetic and high potassium calc-alkaline magmas, basalt mainly. We start from the very beginning of the recent period of activity, which is called the pizzo activity, started 2.5, 1.8 kilo years ago, so during the Roman time. And in this work of 2014, Francalanci and co-workers hypothesized the presence of 2 magmatic reservoirs feeding this beginning of the recent activity, one located about 3 kilometers below the sea level, and another one in between 5 and 12 kilometers below sea level. The shallower magmatic reservoir erupted shoshonetic mafic magma, shoshonetic basalts, whereas the deeper magmatic reservoir erupted high potassium calc-alkaline basalts in minor amounts. Well, we collect this a little less than 3,000 clinopirox from the work of Ubide et al. In 2019, and we applied our machine learning geothermobarometer, and this obtained this distribution of pressure and temperature. And as you can see, the temperature is more or less around 1100 degrees centigrade, but as far as pressure is concerned, we have a major peak in between 3 and 5 kilometers below sea level, which correspond to the occurrence of this magmatic reservoir, shallower magmatic reservoir hypothesized by Francalanci et al. In 2014. Then, if we want to see, there is also possibly another reservoir around 11 kilometers below sea level indicated by this clinopyroxene, but we have to work on this. As I told you, these are preliminary work. Then we go to the very recent magmatic activity Stromboli. We analyzed this eruption of 2019, and the present day activity of Stromboli consists of, also in this case, of two magmatic reservoirs, one closer to the former magmatic reservoir at around 2-3 kilometers below sea level, and the other one is thought to be located at around 7-10 kilometers below sea level. The two magma types are both case basalt, but they are very different from each other. The shallower reservoir consists of the so-called HP magma, which is HP stands for highly porphyritic. It has about 50% phenocryst content, whereas the deeper reservoir consists of the so-called LP magma, which means low porphyritic magma with almost an aphelic magma, volatile rich, and is the feeding magma of the shallower reservoir. In the shallower reservoir, there is also a crystal mash, and this complicated for the process, the structure of the volcano system. So what we have done, we have analyzed this 2019 eruption, and the result of the prediction using our geothermobarometer. We have used 81 dioxide composition of the LP magma, which are represented here. They have a dioxide composition, whereas for the HP magma, we have used 166 clinopyroxene composition, which have an augite composition. And as you can see, these are the result of our prediction using our geothermobarometer. For the LP magma, we have a major peak in between 11 and 13 kilometers below sea level, which correspond to this deeper magmatic reservoir, whereas for the HP magma, we have a major peak in between 3 and 5 kilometers below sea level, which correspond to this shallower magmatic reservoir. In terms of temperature, you can see that especially for the shallower reservoir, for the HP magma, we have a peak around 1100 degrees centigrade, but then we have also a given number of clinopyroxene indicated lower temperature, below 1000 degrees centigrade. And this, we have to work on this to see if it's possible. This could indicate the occurrence of this crystal mash in the shallower magmatic reservoir, which has lower temperature. Then I present the case study we are working on Campi Flegrei with this colleague of ours from the National Institute of Geophysics and Volcanology, Gilberto Saccorotti, Lucia Papalardo, and Francesca Bianco. And we are working on this Campi Flegrei eruptive period. They have a compositional range mainly consisting of trachyte and phonolite, but as you can see, you have also some shoshonite. At Campi Flegrei, the studies recognize four major periods of eruptive activity, from Monte Nuovo in 1548, then 3 other phases after the Neapolitan yellow tuff, the Masseria del Monte tuff, and the Campania ignimbrite. These are the composition of the products erupted during these 8 periods of major eruptive activity. And as I told you before, most of the composition fall in the range of phonolite and trachytes. And what I will present you are the results on the three most violent eruptive periods, which a volcanic explosivity index equal to 5, so they erupted more than or something more about 1 cubic kilometer of material. And as you can see, this drawing below is what has been determined using geophysical survey about the magmatic reservoir below the Campi Flegrei caldera, all interconnected between each other. And these are the results obtained on the Campania Ignimbrite eruption, the Masseria del Monte Tuff eruption, and the Neapolitan Yellow Tuff eruption. You can see that most of the eruption come from magmatic reservoir in between 2 and 4 kilobar below sea level, or 7.5 and 14.5 kilometers, which correspond to this region here of the lower crust where most of the magmatic reservoir do occur. A big difference is the Neapolitan yellow stuff, which is a range of pressure more limited, more restricted with respect to the Masseria del Monte Tuff and the Campania Ignimbrite. Another difference between the Neapolitan yellow stuff and the two previous violent eruption is that also in this case we can see some clinopyroxene indicating lower temperature, both in the case of the Masseria del Monte Tuff and in the case of the Campania Ignimbrite. And this could be, as well as I told about stromboli, they could indicate the occurrence of crystal mash. We have to work on this. As I told you, it's just these are just preliminary work, and we are currently studying this. And eventually, these are the results we obtained on the present day activity from 1900 to present day about the volcano of Etna. We collect something less than 2,000 clinopyroxene from georock, and these are the predictions we obtained using our geothermobarometer. The magma erupted at Etna are mainly basalt or hawaiite and mugearite, and from geophysical survey we see a major magmatic reservoir located at 4 kilometers below sea level, feeding shallower magmatic reservoir inside the volcanic edifice, as you can see from these works which are reported from Bonaccorso and Giuffrida. And what the prediction we obtain from this, from our geothermobarometer, we have a contribution from a reservoir located around 5 kilometers below sea level. Most of the magmatic reservoir feeding the present day activity of Etna is in magmatic reservoir above 0.7 kilometers below sea level. So they are actually within the volcanic edifice, as it's been demonstrated by this work which I presented on the left-hand side diagrams. So, arriving to the conclusion, we think that GAIA is a new deep learning feed-forward neural networks approach based on clinopyroxene-only composition to assess intensive parameter of volcano-plummet system. The application of GAIA to Italian volcanoes yields depth storage conditions comparable with independent geophysical estimates, and this was very important to us. And these pressure estimates reinforce current models of volcano plummet system consisting of physically separated reservoirs interconnected by a network conduits channeling magma en route to the surface. Overall, we are confident that GAIA can provide a robust tool to unravel magma storage, segregation, and ascent condition within the planned system of active volcanoes. And these results, coupled with the time scale of pre-eruptive process using radiogenic isotope and diffusion geochronometry and volatile emission, will set further basis for one of the key research in modern volcanology, that is the prevention and mitigation of volcanic hazard. Thank you very much for your attention.
Okay, thank you very much. Now time for questions for our audience, so feel free to open your mic to ask a question, or you could leave your question in the chat and I could ask a question on your behalf. So any questions from our participants today, please go ahead. Okay, let me start from the very first, from one question. So could you go to one of your slides where you show your validation data set for the deep learning?
Okay, hold on a second.
Is one of your earliest slides that show the performance of the model on validation data set for deep learning? Yeah, this one. Okay, we will start from here.
Temperature pressure.
Yeah. Next slide. Could you go to the next slide, please? Yeah. Okay. Yeah, visually it's very hard to interpret that the R square is 0.99 since the scattering points here. So could you explain a little bit more about the way that the data was treated to produce it?
This is the reason why in the, sorry, I will show you in the test result, I didn't use the pressure value, but only in the x-axis you have the number of data set and we use. This is because as I hold on a second, Gianjo. This is the reason why it appears the data appears very scattered, because most of the data are concentrated at 1 atmosphere, 2 kilowatt, 4 kilowatt, and so on. So when I present the validation set result in this manner, so experimental experimental pressures versus the predicted pressure, it is likely, in this point, there are a lot of data. And so what you see here, it's only the data that scatter. But if you consider 5,000 data, most of the data are along the one-to-one regression line. I don't know if it's clear what I want to say.
And you have been resampling the data set for how many times? Like say 100 times?
For pressure 100 and for temperature 20. So
okay, 100 times. Okay.
Yeah. But
okay.
What I meant in a 4 kilowatt, in this point, there are not just 2-3 data. There are probably 100, 200 data. And that is the reason why the correlation coefficient is so high. So you see only the scatter. And perhaps you can better evaluate this looking at this diagram, where here you have the difference between the experimental pressure and the predicted pressure without our clinopyroxene versus the the number of test data, which are only 5% of the database. So it's a diagram where you can really see that the difference is very little. And this prediction have been made on the test data, not on the validation data.
Oh, I have a quick question. For your test data here, when you count from 1 to 200, it looks okay. So is there any particular preference or sequence that you choose your test data? At least the test data that, let's say, after 200.
Yeah.
That
These are
show very well with prediction. Is there any trick that you did?
No, these are the result of the test data, and I agree. When we go more to pressure more than 8 to 9 kilobar, we have a bigger error. But as a whole, these are 280 data, so the correlation coefficient is slightly worse. But this is because of this. If we would consider only data below 8 kilobar, the correlation coefficient would be much better, and also the error on the estimates. But we use this error on estimates plus or minus 1 kilobar, mainly because of this data. And we are currently trying to improve this algorithm to find out if we can lower the error on the high pressure data.
Okay, thank you. And then there's a question in the chat, and thanks for a great talk. I would like to ask you if there are any sampling bias in the eruption products of the Italian volcanoes that may affect the KDE of GAIA application.
Well, a sampling bias, of course, there can be a sampling bias, but we collect all the data available on GeoRock. So we use, these are not the data we made ourselves, but we use the clinopyroxene composition available on GeoRock for this volcano, and we apply the geothermobarometer on this data. And of course, there could be some eruption which are not very well represented, other are more represented, but this is what we had available when we made the geothermobarometer. It's the same story for the library of experimental phase relations. We had to use the available data, and most of the available data are 1 atmosphere, 2 kilobar, 4 kilobar, 8 kilobars. So we have to live with that. This is something we are thinking to improve in the future, to see if there is a way to improve this library and be able to train the machine learning with a more uniform pressure distribution.
Okay, another question from our in the chat. Actually, there are 2 questions. One is quick one. Why is thermobarometer, the A is capital, is capitalized in the middle of the word?
Yeah, this is a funny story because, okay, I don't like the acronyms they choose. It wasn't me, it was Luca Bindi. And to make GAIA correspond to the geothermobarometer, they had to capitalize a letter in the middle of thermobarometry. But this is just, well, it's something which I didn't like, but I was the minority. 3 out of 4 like this acronyms, GAIA.
Right. Does it have any meaning in Italian or
GAIA is the earth, geology in Greek is GAIA.
Okay, makes sense. Okay, then there's a science question. So they ask that if the calcium ASCOLA is involved, the total cations of a CPX will be less than 4. So will this have any impact on your model?
Hold on a second. Say it again. Calcium. It was about
Yes,
the
calcium is involved. The total cations CPX. Maybe use your next. Okay, this slide is okay.
Oh, is it okay or the other one?
Okay. Dr. Chanleve, could you further explain? Could you further elaborate your question?
Hello. Hello, can you hear me?
Yeah, please go ahead.
Yes. If calcium, calcium ascorate, the total cation is 3.5. So if the N member is involved, the total cation will be less than 4.
Sorry, I didn't get your question.
So you have
Okay.
so you have an assumption. The total cation of CPS should be 4, right?
Yeah.
Actually, if calcium ascorate is involved, the total cations will be less than 4.
If I didn't understand the component you mentioned, calcium.
Calcium ascorate.
Calcium. Cermak.
It's in the chat. Actually, I don't read it.
Okay. Let me.
Sorry, John. Gianju, did you understand which component it was referring to?
You don't have it. You don't have it in your list.
Okay.
Yeah.
So, which is the component you're speaking of? Calcium?
Yeah. So you don't have that. Actually, you don't have that.
But which is the component it was referring to? Do you understand? Do you get it? Because I don't.
I think it's fine. So for this one, yeah, you don't have that component.
Well, I didn't understand the question, but the clinopyroxene components were selected by Luca Bindi, which is has very long expertise in mineralogy, and he chose to work on this component for clinopyroxene.
Okay, thank you.
But Dr. Chanlave is that the calcium ascola is, let's say, the component is more significant at the higher pressures, because I think here that is that true? I think this is.
Yeah.
Okay.
Probably true. Yeah. Thank you.
Yeah. That doesn't really apply here. So it's one CPS component that could occur at a much higher pressure, like 6 GPa or 10 GPa or even higher. But in this system, that should not evolve with that.
The selection we made is for data set less than 10 kilobars. So
yeah, should be okay. Okay, any more questions from our participant? Actually, I have another curious question, quick one. So for the catchment model, I'm not a volcanologist. So for the catchment model, in terms of volcanoes, that you said that universally applies to almost all the volcanoes in the world, or
Yeah.
does it only or it is also case to case according to different tectonic units?
As far as we understood from the work of Cashman, where she determined the occurrence of several intracrustal magmatic reservoirs, this is what we have determined on the basis of a geophysical survey on the 5 Italian volcanoes we've worked on. If the conclusion of Cashman applies to all the volcanoes around the world, I cannot say, but in the case of the 5 Italian volcanoes, yes, and not because of the result of the prediction of our geothermobarometer, but based upon geophysical surveys, where they indicate the occurrence of several magmatic reservoirs within the crust.
Okay, so this let's say according to your interpretation, that what's the percentage of volcanoes that people have already, as a know pretty well, whether it agrees with the catchment model or not? Because most of the volcanoes probably people have not looked at so much detail that could tell yes or no. It's like only like 5 volcanoes out of, let's say, 10,000 volcanoes in the world. I don't know.
Well,
I don't know what's the number.
This is a number I cannot tell you. I mean, it's something that we focus on these Italian volcanoes, and we found out that the model of Cashman was pretty well in agreement with what we found in these 5 Italian volcanoes, and also on the volcanoes she worked on. If this is a common characteristics of all volcanoes, I cannot say, but I think it should be pretty common also in most of the volcanoes to have multiple magmatic reservoirs interconnected each other.
Okay. Okay, that's great. Okay, I think this is about time. It's about 1 hour. It's perfect. And thank you very much, Professor Tommasini, and thanks everyone for your participation. So before I turn the meeting off, so could everyone, if you can, could you open your video and smile and show your appreciation to our speaker today, so that our speaker could see your face for today's webinar. So could you open your video and let's wave and smile to our speaker today. And then I'm going to turn the video off in about within 1 minute. Okay. Mm-hmm.
Okay, thank you very much again for inviting me to give this seminar.